Okay, so again, I'm going to lecture to an empty classroom because I feel like I didn't give such a clear explanation the other day. So today we're going to be covering the climax of the course, which is the Theorem of Ascoli-Arzela, and we'll also do the great theorem of Stone-Weierstrass. Okay. So here we go. So here's the statement of the theorem. Suppose you have a sequence of complex value functions on some set K. If K is compact, if the f sub n are pointwise bounded, right? So that means that at every point there's a bound, right? At every point there's a bound for the absolute values of the values of the f sub n at that point. And if the Fn, this family is equicontinuous, then there exists, then f sub n has a uniformly convergent subsequence. And at the same time, we get that f sub n is in fact uniformly bounded, not just pointwise bounded. Right? So there's an M that works for all points, and all f sub n dominates all the magnitudes of those values. Okay. So this is, like we said before, this is a generalization. It's like an analog of the Bolzano-Weierstrass theorem that said that if you have an infinite sequence in a bounded region of Rk, then you're guaranteed a convergent subsequence. Right. So here we've got, this is a statement about functions. If we satisfy these conditions, then our sequence of functions has a uniformly convergent subsequence. Okay. Okay. So we'll do this in two parts. We'll first show that Fn is uniformly bounded, and in my notes, I have this picture. Of a bunch of dots. And it says trivial. So let's see that it actually is trivial. Okay. So the main thing that we're going to use is equicontinuity. By equicontinuity, we know that given any epsilon, so fix an epsilon, fix an epsilon. By equicontinuity, we know there exists some delta such that whenever 2 points are within delta of each other, then, so if this happens, then the distance between fnx and fny is smaller than epsilon for all n, like for all the functions, right? So it's equicontinuous, right? We can control the variation of all the functions. So, cover K with delta neighborhoods. Right. So cover each point in K with a neighborhood of radius delta, and since K is compact, we know that there exists a finite subcover. There exists a finite subcover n delta xi equals 1n. Okay. Okay. And then so there's a finite number of points. There's a finite number of points, and whose delta neighborhoods cover all of K. So you can probably guess what we're going to do. You say, well, look, we have pointwise boundedness, right? So since the f sub n are pointwise bounded, we know that at each point there is some maximum value, right? The values of the f sub n all lie between here and here at x1, between here and here at x2, and between here and here at x3, right? Okay, so and further, by equicontinuity, we know that in this neighborhood, every function doesn't vary by more than epsilon, right? So the magnitude of the values can be in this neighborhood is this m plus epsilon. In this neighborhood, be this m plus epsilon, and this would be this epsilon, right? So you see that it's easy to get a uniform bound. Okay, so since the f sub n are pointwise bounded, we have mi such that fn xi is less than mi, right, for I equals 1 n, right? And then for any x in k, well, it must lie in one of these delta neighborhoods, right? So x must lie in some delta neighborhood of some xi, right? And so the absolute value of fn x must be controlled by mi plus epsilon, right? If you lie in that I, the delta neighborhood of xi, right? So for that I, so fn x, is going to be less than or equal to the max of the mi plus epsilon. So we found our uniform bound. Okay. So that's how you get. That's how you see that the f sub n are uniformly bounded, and now we'll see that the fn has to have a uniformly convergent subsequence. And the argument is kind of similar. Okay, so we're going to use the following fact, which maybe we'll leave as an exercise. That since K is a compact metric space, there exists a countable dense subset called E sitting inside of K. So it's a countable set inside of K whose closure equals all of K. In other words, every point of K is either in E already or is a limit point of E. Okay, and this is it's an easy exercise to do. You just say, well, since cover every point of K with neighborhoods of radius 1. There exists a finite subcover. So take the centers of all those. Take the centers of all those neighborhoods. Okay, and then cover K with neighborhoods of radius 1/2. There exists a finite subcover of that cover. You take the centers of all those guys, right? And so continuing in this way, you get a countable collection of points such that every point in K, for every point in K, you can find a sequence that approaches that point, right, by looking at what neighborhood that point is in, which neighborhoods that point lies in. Okay, so that's actually pretty easy. But this allows us to use the theorem that we had the other day. That so by the previous theorem. You remember the last time we showed that if you have a sequence of functions on if you have a pointwise bounded sequence of functions on a countable set, then you're guaranteed a pointwise convergent subsequence. So by the previous theorem, there exists a subsequence fnk, which is pointwise convergent on E. Okay, and I'm going to claim that this sequence is in fact uniformly convergent. fnk is in fact uniformly convergent. So again, we're going to use equicontinuity. So okay, so choose. So suppose that somebody gives you an epsilon, and then by equicontinuity, there exists a delta, such that if the distance between 2 points is less than delta, then the distance between fnk x and fnk y is less than epsilon over 3, say, for all k. Okay. Now again, we're going to cover E this time. We'll cover E with delta neighborhoods. Okay. But since E is dense in K, that means that by covering E with these delta neighborhoods, we cover all of K as well, right? Because, like we said before, either the points of K are either in E or they're limit points of E. Well, being a limit point of E means that you can find points of E that are less than delta distance away from you, and so you will be covered by the delta neighborhood of that point in E. Okay. So since E is dense in K, you see that this covers, this also covers, this is an open cover of K as well. Okay. So what that allows us to do is we get a finite open cover K, but where all the points are, all the centers are points of E. So n delta I equals 1 P. Okay. So this is good. Okay. So remember what we're trying to do? We're trying to show that we have uniform convergence of these guys. Okay. This is just a finite set. So we already have pointwise, right? We have pointwise convergence on all of E. In particular, we've got pointwise convergence on these P this finite collection of points, E1 through EP, right? So that basically gives us uniform convergence. That gives us uniform convergence on this finite set, and then we use equicontinuity to get uniform convergence on the entirety of K. Okay, so let's do that. So since the F and K are pointwise convergent on E, they are, of course, pointwise convergent on E1 through EP. Right? Okay. So we can choose, there exists an N such that if K and L are bigger than N, then F sub N K EI minus F sub N and L EI is smaller than epsilon over 3 at each of those points. I equals 1 to P. Right? We have convergence on each of these points, right? So we can do this. we can do this at each of these points individually, and then we just take the max. We can find an N that works for each EI, and then we just take the max of those N's to get this N. Right? So this N is actually some max of some N sub I equals 1 to P. Okay, so we can control the distance between these pairs of functions at each of those points, and then we use the equicontinuity to get this control on all of K. Okay, so let's do that. Let's do it here. Let's do it here. Okay, so then for any x in K, if K and L are bigger than N, we know that Fnkx minus Fnlx is, by the triangle inequality, smaller than Fnkx minus Fnkei plus Fnkei minus Fnlei plus Fnlei minus Fnlx. Right? For some EI where x lies in the delta neighborhood of EI, right? So, right, we have this finite open cover of K. X is in K, so it must lie in one of these. It must lie in one of these neighborhoods. Okay, and then what we see is that, well, the pointwise convergence gives us that this is less than epsilon over 3. The equicontinuity gives you that this is less than epsilon over 3, and that this is less than epsilon over 3. So the whole thing is less than epsilon. Okay. So right, which is uniform convergence. Right? So somebody gave us an epsilon, and we found an N, right, using that pointwise convergent subsequence on the countable dense subset. We found an N such that for any two indices past that n, the difference between these two functions is less than epsilon. So that's that is the great theorem of Ascoli-Arzela. Okay, so I think the proof is pretty simple, but it involves a lot of things. Maybe it's not simple. I don't know. It's not simple, but it's. I hope you like it. Okay. Okay. So that was a sort of compactness statement, right? Saying, under certain conditions, whenever you have an infinite sequence, you have a uniformly convergent subsequence, right? This is like a sequential compactness statement. The last thing that we're going to do, the theorem of Stone-Weierstrass, is what could be called a density theorem. So let me release. Okay. Okay. So here it is. The theorem of Stone-Weierstrass. Okay. So given any function in the continuous functions on some closed and bounded interval AB, there exists a sequence of polynomials, Pn, such that Pn converges to F uniformly on AB. Okay. So, so given any function, you can find polynomials, right? So given any function on AB, right, you can find a sequence of functions, a sequence of polynomials, so that given any epsilon 2, there is a time past which all the polynomials lie inside that tube. Okay, so this is that's what it says. So just a remark. Recall that uniform convergence is the same thing as convergence with respect to the sup norm metric. Okay. On CAB. Right. So what this is saying is that given any point, given any function, you think of the function as a point in this space. There is a collection of polynomials that will converge to that point with respect to the sup norm metric. Okay, so this is a density statement, right? That you can reach any point using polynomials. In other words, the polynomials are a dense subset of the continuous functions on AB. Okay, so this is same thing as saying polynomials are dense in CAB with respect to the sup norm metric. Okay. Okay. So this is a pretty cool theorem, but what's even more important about it, I think, is the method the method of proof. Okay, so the technique used is one that is used frequently. It's used all over the place in analysis. Okay, so let's talk about that. Okay, so another comment is that without loss of generality, we can assume that AB is just the interval 0, 1. Right? You can rescale your polynomials. You can translate them and then dilate them as needed. And then the second thing is that we can also assume that f at 0, f at the endpoints takes the value 0, right? Because if we can do it for functions that look like this, if we can do it for functions that look like this, and if somebody gives us another function, just subtract off a line, which is a polynomial, then get the polynomial approximation for this guy, and then add this line, which is a polynomial, back onto it, and that will give you polynomials that converge uniformly to this guy. So that we're not losing anything by doing that. And then the last thing we're going to assume is that f of x is 0 outside of 0, 1. Okay, so our function is 0 at the endpoints, and we're going to assume that it just continues on at 0. We define it on the rest of the real line by making a continuous function that takes the value 0 outside. Okay, and the point of doing this is that this makes f uniformly continuous on all of R. Okay, so we've got it defined on all of R, and we say that it's uniformly continuous. Okay, so okay, so the proof uses something called the method of approximation of the identity. Okay. So we'll explain what this means. This word identity means basically the multiplicative identity, something like the number 1. Right? So we're going to approximate something that we think of as the number 1. Well, what that is, we'll explain in a couple minutes. Okay. So let q sub n x be the function 1 minus x squared to the n on -1, 1. Okay. So it's just you take 1 minus x squared, right? You've got this parabola going downwards, and you chop it off there. You call that thing q sub n. Okay. That's actually not what we want as q sub n. We're going to multiply it by a constant. So the constant is going to be 1 over the integral of 1 minus x squared to the n from -1 to 1. Right? And the reason we do that is because we want this. We want each of these functions to have an integral of 1. Okay. So we scale it. We scale it in some way so that the area is actually 1. Okay. And if you look at these guys, they start to look like this, and then they start to get taller and taller. But we want them all to have area 1. We want them all to have area 1. Okay, so a couple of observations. First is, of course, that the integral is 1. And then the second one is that for any delta, q sub n converges to 0 uniformly on this interval. Okay. So if we look at if we choose any delta, then on this region here, the q sub n are going to converge to 0 uniformly. Okay, so the reason for that is that it's easy to see, so exercise. Easy to see that C sub n is smaller than the square root of n. Should I do it? Okay, I have infinite time. I should do it. Okay, so not an exercise. So first, why? So why? One, we'll claim that C sub n is less than the square root of n. And we just calculate, do some estimation. Okay, so looking at 1 minus x squared dx, we say, okay, well, this is an even function, so this is the same thing as twice the integral from 0 to 1 of the same integrand, right? And now let's make the let's make the domain of integration smaller. So instead of integrating from 0 to 1, we're going to integrate it from 0 to 1 over the square root of n. Now this I'll leave as an exercise. We can see that this integrand, 1 minus nx squared, so 1 minus x squared is greater than equal to 1 minus nx n times, 1 minus x squared to the n is greater than or equal to 1 minus nx squared on 0, 1. So exercise. And if you calculate that, that turns out to be 4 over 3 roots of n, which is of course bigger than 1 over root n. Okay, and of course C sub n is the reciprocal of that, so we get that C sub n is less than the square root of n. Okay, now okay, so we're looking at q sub n, so we see that q sub n x is smaller than the square root of n 1 minus x squared to the n, right? But since we are in right, since we're in this region, we see that 1 minus x squared is less than or equal to 1 minus delta squared, right? Because delta delta is some non-negative number that's less than this. We're subtracting off the square of something smaller, so it gets bigger. Okay. So this is less than or equal to the square root of n times 1 minus delta squared to the n. Okay. And the limit of this, if you take the limit of this as n goes to infinity, you get 0 by L'Hopital's rule, say. Okay. So that gives us that right, for all the points, in here, right, the q sub n go uniformly to 0, right, because they get squashed by this sequence of numbers. Okay. So Right. So what we see is that, right, we have this, we have these q sub n guys, and their integrals are all 1, and they are decaying really quickly. Right, we have uniform convergence to 0 outside of any neighborhood of the origin. Okay. And so what you see is basically that the mass of these functions is getting bunched up near 0, right? As n goes to infinity, right? They all have integral 1, but that 1 gets more and more concentrated at 0. And so you can think of these guys as approaching in the limit the so-called Dirac delta function, this sort of imaginary function that has an integral of 1, but is equal to 0 everywhere away from the origin. Okay, so it's not really a function; it's what's called a distribution. But physicists created it and used it before mathematicians came up with the theory of distributions that explains it, or sort of made it mathematically rigorous. Okay, and that Dirac delta function you want to think of as the identity that this sequence of functions is approximate. Okay. So what are we doing? We start off by creating the approximation of the identity. Okay. It's something that converges to the Dirac delta function. Okay. So next thing we do. So now define Pnx as the integral from -1 to 1 of f x plus t q sub n t dt. And these are going to be the polynomials that the theorem is looking for, that we're looking for, right? So these are going to turn out to be polynomials, and they will converge uniformly to f. So the way you want to think of this again is suppose you had over here the Dirac delta function, right, which gives you a mass of 1, but only when t is equal to 0. In that case, when you took this integral, well, what would happen is that you would basically recover your function, right? You would have a 0 everywhere, but suddenly when t is equal to 0, you get a massive 1 that gets multiplied by your f of x and allows you to recover f of x. Okay, so that's not possible, but we do have these things that approach it. Okay, so 2 claims. The p sub n are polynomials, and second, the p sub n converge to f uniformly in 0, 1. Okay, so as for the first claim, so p sub n is the integral from -1 to 1 of f of x plus t q sub n t dt. And you recall that the domain of f, the support of f, where f is only non-zero when x plus t lies in 0, 1. Right? So x plus t has to lie between 0 and 1. In other words, t actually lies between 1 minus x and negative x. Okay, so we can adjust the domain. We can sort of correct the domain, negative x to 1 minus x. Right? Because remember, f was supported on 0, 1. Okay. Okay. So now we do a change of variables, and we get that this is actually the integral from 0 to 1 of f of t q t minus x dt. Okay, so that's just a change of variable. Change of variable, and now this q sub n, remember, is c sub n 1 minus t minus x squared to the n, right? So we get the integral from 0 to 1, constant f of t, we get this. Okay. And you notice that this is actually, if you think about it, you'll see that this is actually a polynomial in x. Right? When you do the integration, right here from this thing, you're just going to get powers of x. You're going to get even powers of x, right? And when you integrate with respect to t, you're just going to get some coefficients on that. Okay, so you're going to ultimately, sorry, this turns into a polynomial of degree less than or equal to 2n. Okay. So it's a polynomial. It is a polynomial in x. Okay. Okay. So we just have one last thing to do, which is to show that the p sub n converge to f uniformly. And this is where we get to see how the method of approximation of the identity really comes through. So let me go backwards because we're going to need a lot of space. Okay. So okay. So start off by fixing an epsilon, right? We want to show that there exists an n such that if we're past that n, then p sub n of x is within epsilon of x for all x in 0, 1. Right? In other words, that we lie within the epsilon tube around f of x. Okay. So let's look. So well, if we look at this thing, this is by definition the integral of q. Oops, let me write this way. F x plus t q and t dt minus f of x. Okay. And now we play a funny trick, which is we multiply this thing by 1. Okay. We multiply this thing by 1, and we pull the f of x inside. Okay. Now we can combine these two integrals together, and we get, this is the integral of f of x plus t minus f of x times q and t dt. Okay. So the fact that the integral of the q sub n was 1 allowed us to slide the f of x into here and get this single integral. And we're going to break this integral into two parts. Okay. So by triangle inequality, this is less than or equal to this. Remember that the q sub n is a positive, so we don't need the absolute values. Okay. And now we're going to break it into two parts. On the first of which, we can use the uniform continuity of f to control the integral. And on the second integral, we'll use the uniform convergence of the q sub n to 0 to control the integral. Okay? So this is exactly how the method of approximation of the identity is used. Okay? So we say, okay, we're going to break this into two parts. This integral here is the same thing as, so we break it into the part where t is less than some delta. And also the part where t is bigger than delta. You see what we're doing? We're splitting it into we separate the part on which we have uniform convergence to 0, right? And then we have to deal with this part, but we can, on that part, we'll choose delta small enough that that this is tiny, right? By using the uniform continuity of f. Okay. So right, so we can do this. We can do this for any delta. So choose delta so that if t is less than delta, then f of x plus t minus f of x is smaller than epsilon over 2. Right? So just choose your delta from uniform continuity, right? It's the delta that guarantees that if 2 points are within delta of each other, then the difference is smaller than epsilon over 2. So using uniform continuity, choose your delta in this way. So what does that give us? That gives us that this thing is smaller than epsilon over 2 times the integral over this thing of q and t. Right? And we have this part also. Okay. Well, you can see what's going to happen. Over here, we don't have control over the difference, but we don't need it. We're just going to say, well, look, f is now f is bounded. Right? F is a continuous function, so it's bounded by some m on 0, 1, right? And so we'll control this thing just by 2m. Okay. So we get that this is less than or equal to epsilon over 2 times this thing. But I'm going to throw that thing out. That thing is smaller than the integral of q and t over the whole integrals negative 1, 1. Right? So right? I should say it's just bounded by m everywhere. Right? It's bounded so that this thing is controlled by the integral over negative 1, 1, and that integral is just 1. So we can get rid of this. This is 1. And then this is smaller than 2m times times the integral of q and t dt over this region. Okay. Now we know that these qn go to 0 uniformly. So qn go to 0 uniformly on that region. So we have that the limit of these integrals as n goes to infinity equals the integral of the limit, but the integral of the limit is 0. Right? So, so choose n such that n bigger than n implies that the integral is smaller than epsilon over 4m. Okay, right? And you see what happens once you make that choice. Once you do that, then this thing is going to be smaller than epsilon over 2 plus 2m epsilon over 4m, right? Which is epsilon. Okay. So, yeah, it's a little bit bad board work, but once you've chosen this m, then you get this inequality here. Okay. So you found the n that shows that the distance between p sub nx and f of x is less than epsilon over the whole interval. And so you found polynomials that converge uniformly to this continuous function. Okay. Okay. So that's it. I hope you got something out of the course.